The grades, you probably are a little disappointed with the grades. They weren't stunning. Um, there wasn't like a typical mistake, except I did see quite a few people not remember to do the chain rule. And if you look at the first one, maybe you memorized that the derivative of inverse sine of an angle is 1 over the square root of 1 minus that angle squared. But then that angle has a derivative of 2, and you've got to multiply by 2. Chain rule just happens everywhere now. There's just almost not a problem we ever do without chain rule anymore. Also, this happened on number 2, because when you do the derivative of arctan, if it was arctan x, the derivative would be 1 over 1 plus x squared. But it's arctan cosine theta. So cosine theta goes in here for x, and the cosine of theta has a derivative, negative sine theta, so you have to multiply by it. Now on number 3, that was L'Hopital's rule. You did have to apply it twice. But because when you substitute pi halves in there for pi, you do get 0 over 0. So you apply it the first time, and you have something that does not look just a whole lot better than the original. You get this right here when you simplify. But nevertheless, plug in pi halves again, you still have 0 over 0. So when you take the derivative again, you get negative sine theta over 2 cosine 2 theta. You pick up another 2 by chain rule again, which is negative sine theta over 4 cosine 2 theta. And both of those can be evaluated by direct substitution right here, and you do just get 1/4. All right, now on this last one, this was using these. And all of these, there'll be problems on the test next week, like all of these. Absolute max and absolute min. First of all, you need to note F is continuous on the closed interval and differentiable on the open interval, which I did not say, but I sure should. Well, yeah, differentiable on open. Well, if that's true now, then the derivative here, when you set it equal to 0, will give you the only possible place where during that interval it could have attained a max or min. So it's going to have an absolute max and an absolute min either at an endpoint 0.5 or when x is 2. So you just evaluate here. The biggest was 16, so it's the absolute max. The smallest was 7, so it's the absolute min. Yeah. All right, so see me if you have any problems with the grading of this. I've got it right here. And if you have further questions about grading, then you should come see me in my office or something like that. The problem is if we work out a full problem, there's about 30 minutes at least gone. And today I need the period to talk about optimization and introduce that to you. All right, so I'd like to start with that now. And we're going to take the first part of class to kind of step back from the problems a minute and examine them and see if we can figure out why this technique is a big deal. What difference does it really make? Okay, to be able to optimize the use of something. So let me show you. I've got a problem I think we'll show this in kind of a graphic way. Okay, here we go. Suppose that here's our setup. We have someone who has purchased as many feet of fencing as they can possibly afford, and they've got some livestock that they want to let graze by a river, but they want to enclose the area with fencing. So they spend all they have, 2,400 feet of fencing is what they've got. And they want to use it to enclose the biggest area they can for obvious reasons. to maximize the grazing space, and they don't need it along one side of the rectangular area because they have the river there, they want access to the river. Okay, so this is the setup right here, 2,400 feet of fencing. Now, when you just superficially look at the problem, you might think, well, what difference does it make? Just as long as you use up all the fencing, you've maximized the area that is enclosed. But when you think about it just a little bit further, that turns out not to be the case. Now, I've drawn here 5 different scenarios where you use 2,400 feet of fencing. So look at this one for a minute. 1150 along this side plus another 1150 on this side would be 2,300 plus 100 along this side. There's the 2,400 feet of fencing, right? Okay, so if I were to figure out what the area of this space enclosed is, I would say 1150 times 100. So that would be, the area would be 1150 and then times 100. So 115,000 square feet. Okay, nod your head if you're with me so far. Everybody got this? Okay, well, suppose that we thought, well, maybe we ought to just use 2,200 on the really long side, and we only have to use 200 on the edges. Those 200 would be added to this. Now we're at 2,400 again. So we've used the same fencing in this configuration, and this time it's 2,200 times another 100. So 220,000. You see how we've increased the area enclosed? I know this is a weird looking configuration, but I just want to show you the extreme examples. In both cases, we've used all the fencing we purchased. Okay, so let's say we go to something that is more like a traditional kind of rectangular shape. Suppose I use 400 along one side and 1,000 here and 1,000 here, again using 2,400. So the area enclosed here is 400 times 1,000. Now I've got an area of 400,000. Okay, we're on a roll here. That's a lot more area, isn't it? A lot more grazing space for my livestock. Okay, so are you starting to be convinced that the configuration does matter, doesn't it? You know, same money spent on fencing, but way different result in terms of grazing space. Okay, here's another way we could do it. 800, 800, 800, 3 times 800, there's 2,400. So what would be the area enclosed here? 640,000. We're still increasing the area, aren't we? It's going up every single time. So we have, I wonder if we're getting close to maximizing our space. And let's try this over here. I could do 400, 1,600, 400. 400 and 400 is 800, and 1,600, there's 2,400 feet of fencing. So this time the area would be 1,600 times 400. This time I've got 640,000 too. So that's interesting, different configuration, but I've enclosed the same amount of area. And by the way, when I did this, I counted out the boxes, you know, where each box had was 100 feet on each side. And so roughly it does sort of look like those spaces. Okay, so you bought the fencing, you've drawn it out, you've realized, wow, it makes a difference. So how could I maximize that area? How could I maximize the area? Now, if you think about it, the area is just length times width. That's a nice, easy equation. And so let's do a little bit of math. Now, here's the problem again. Now I'm going to let these be unknown. We've got widths, and I've just randomly called these widths. They could have been lengths, and that could have been width. However you want to think about it, it really doesn't matter until we get the answer, and then it'll matter where we put the numbers. But but that could work out either way. All right, so let's see what we have. We have W plus L is 2,400, right? So 2W plus L is our 2,400 feet of fencing. Now that is fixed, isn't it? And we want to maximize the area. Well, area is length times width, as I said. But here's the thing. In a problem like this, you got these two equations. Now, this is the one we want to differentiate. We want to take the derivative, set it equal to 0, find the max or min point, evaluate it, you know, like the closed interval technique, like that. But we have another equation. Now, this is called like an initial constraint. And what it's going to allow us to do is get L alone in terms of W and plug it in there so we've only got one variable, which will be nice. We don't want to use product rule. We don't have to. Okay, so let's take this first equation, this constraint, because we cannot have any more fencing. We've maxed out on that. So L is 2,400 minus 2W. So that now my A equation is 2,400 minus 2W times W using substitution. And what that is 2,400W minus 2W squared. Now looking at that, we are happy because we know that if I drew this out on a grid, what would it have the shape of? A parabola. Opening up or opening down? Opening down because of the -2, right? And parabolas that open down do in fact have a max, don't they? So this is going to be a very doable problem. We just from our intuition, our math intuition. Okay. So let's see. Now, what we want to do now, we certainly have a differentiable function. We have it's continuous, a continuous function on all of R, and it's differentiable on all of R. So I'm just going to put a note here. A is continuous and differentiable on all of R. Okay, so we want the derivative. Well, A prime is going to be 2,400 minus 4W, right? So we set it equal to 0. So that means 4W is 2,400. So that means W is 600. Now, I know that our intuition told us we had a down opening parabola. This can only be a max. There's certainly no min. It's going to negative infinity on both ends of the parabola. But nevertheless, isn't it interesting to note here that if I took A double prime, what would it be?
24 or
-4. Okay, -4 is always a negative number. It's always concave down. Therefore, we know a max is formed. Now, in these problems, I do want you to write a little note somewhere on that just to check that you have, in fact, verified that this was a max and not a min. We certainly don't want to minimize that area, but that's kind of ridiculous, right? I mean, yeah. So note A double prime equals -4, which is always negative, which implies it's always concave down, which implies a max is formed. This is kind of just a side note just to verify that that is in fact a max. Now, we want the dimensions, plural, and we also want what is that max area formed. You know, remember we achieved an area of 640,000, just kind of guessing around on the previous page. Wonder if that's it or if there's a better one. So let's substitute this W into the equation for L. L was 2,400 minus 2W, so it's now 2,400 minus 2 times 600. So it's 2,400 minus 1,200, so it's 1,200. So the dimensions of the field that maximize area are 600 by 1,200. Now, the 600 has to be these sides here, and the 1,200 has to be this side. So at this point, it matters which is which. Okay, so making the max area equal to 600 by 1,200 so it's 720,000. And this is in square feet. So in fact, I mean, we were coming sort of close over here at the two configurations for 600 and 40,000, but we could do a little bit better. Now, do you see how, if you're the one who's purchased the fencing and you're putting your livestock in there that you've also paid for and take care of daily, you would definitely want to know this, wouldn't you? You would want to do the smart thing, not just use all your fencing and think, done, I've used it all, so it must be max. You see? So this is where you move from a person who just works hard to a person who effectively works hard and maximizes their effort, you know, maximizes their effort to achieve whatever your goal is. Okay. Okay, so that's why it's important. Now, I know this is a simple little problem, and this, like in related rates, these problems are each different from each other. But there are similarities. The similarities will be that often a picture helps, A. B, you want to write statements about what you have and what it is you want to maximize or minimize it. All of them are maximize or minimize problems. So it's the maximizing or minimize equation. That's the one that you're going to want to differentiate and set equal to 0 and all of that kind of thing. And the other one will be used as a way to simplify your maximizing equation. Maybe get it in terms of one variable like we did here. Okay. Do you have any questions before we move on about this? Yes, Amanda.
Does anything different happen mathematically if we use that as like a blueprint for how to do these problems? If we're finding the minimum, is there anything different?
No.
It's the exact same.
It's the same thing. Yeah. And we want that sometimes. We want to minimize cost or something like that, or time required to do something. Or, yeah. No, it's the same technique. Yeah, it is. Yes.
So if you know how you solve the equation or move the equation in terms of L,
Yeah.
could you do it in terms of W?
You could.
But it would be divided by 2.
You would be dividing by 2, so you'd have that fraction, but otherwise it would work out somewhat. Yeah.
Just wanna make sure.
Yeah, there's no way to, there's no hard and fast rule of which letter you do in terms of the other. Whichever makes sense to you. Okay, was there another question? Stephen, was your hand going up? No? Andrew, was it? No? I thought I saw movement over here. All right. Any other questions? All right, so let's try another one. Now, I told you about this one, and this one's in the book. It's just one that I really like so much, and it's one that, you know, you can imagine would be very important to manufacturers of liquids, people who are selling liquids of any kind. You want to minimize the surface area of a can, right? You want to do the configuration. I know that we kind of think those tall, thin ones are elegant, but they're wasting material when they do that, aren't they? They could be better by having a little shorter one. They could get more liquid in a smaller surface area. And so what we want to prove that, we want to think about, you know, if we were manufacturing cans, lots and lots of cans to sell, how would we maximize the volume of that can or minimize the surface area of that can? Okay. Now, there are other parameters involved that we're not going to consider today. And one of them is, if you have a can that has a pop top thing in it, you have to make the top thicker so that, you know, you don't cave the can in when you punch that little thing in it. You know what I mean? Okay, but we're going to assume that our can, and also some cans, like cans of oil, you know, well, it used to, I guess they're plastic now, but it used to be they were cardboard on the outside with kind of glazed with a foil kind of thing, and then they were metal on the top and bottom. So if you have different materials on the sides and on the top and bottom, then each thing costs a different amount per square inch. And so you take that into consideration. But all this is stuff that you can put into your equation, and you can take it into consideration when you solve. So for the purpose of today, all the materials, top, bottom, sides, same material, same thickness. Okay, so, and we're going to talk about a can that holds a liter of oil. So we have, this is example 2 in your book. A cylindrical can holds 1 liter of oil. And it turns out it's really immaterial how much the can holds, because we could have made it any amount and still we'll be able to find the dimensions of the one that minimizes surface area. Find the dimensions of the can. That minimize the cost of material used. To manufacture the can. So a very, very simple sounding problem, isn't it? All right, so we're going to have to figure out, well, it's surface area that we're going to want to minimize, right? But we also need something that we know. And what we do know is that the volume of it is 1 liter. So we know the volume equals 1 liter. Okay, now 1 liter, and let's say that the dimensions of the can are in centimeters. Then 1 liter is 1,000 cubic centimeters. Okay, now, how would we write? We're going to write surface area. It's going to be in terms of radius and height of the can. So we need a formula for the volume of the can, and this is something I would not give you because it's a cylinder, and the radius remains the same, so all you have to do is multiply the area of the base times the height. All right, the base is a circle. What's the area of a circle? Pi r squared times a height. So that's volume. So 1,000 equals pi r squared h. Okay, now let's look at what the can might look like. Okay, from here to here, it's got some height. And then the radius of the base and the lid, they're both R, right? So that's kind of all we could draw really at this point. So we want to minimize. Now in the book they call this area, but I like to call it SA for surface area. It just reminds me we're in 3D. Okay, so the surface area, okay, it's got a top and it's got a bottom, and both of them are circles. Okay, so we agreed the area of the circle was pi r squared. So there's 2 pi r squares. Now we've got to get the lateral area of these sides. Well, they're h in height, right? So then h is going to be times how long around the can is. Well, if you cut that can on one side and lay out the side, it's just that rectangle, and the length of the rectangle it has to be the circumference of the circle. What's the circumference of a circle? 2 pi r, yes. So 2 pi r is the circumference, of that's the distance around, and then times h, right? Okay. Now, again, I've got an equation, and I've got a couple of variables over here, and I would like to simplify that, just have a moment. And I'm going to use my initial constraint here, that it holds 1,000 cubic liters of oil. And so you see how I could solve for h on the right-hand side and get it in terms of r. So at this point, when I see these 2 variables over here, I'm going to come over to the left and say h must be 1,000 divided by pi r squared. And I'm going to use that to substitute in over here, so that my surface area now remember, we do a lot of fooling around with the equation before we ever differentiate. We've all seen the logic in that, right?
Mm-hmm.
We want something simple. So the surface area is 2 pi r squared plus 2 pi r times h, which is now 1,000 divided by pi r squared. Now I'm going to put the 2 pi r over 1 since I'm multiplying it times a fraction, and let's keep simplifying. 2 pi r squared plus, well, okay, the pi over pi is 1, isn't it? And this r cancels one of these in the denominator. So I now have, on the right-hand side, I've got 2,000. Now I want to differentiate it, so are y'all okay with me saying r to the negative 1 at this point? Yeah? R is still in the denominator because there were 2 of them. One of them canceled with that, so I have an r in the denominator, so I'm saying r to the negative 1. Yes, okay. Now we're ready to differentiate. We've got an equation in just one variable. So SA prime would be, now pull the 2 and pi are constant multipliers out in front of r squared. So pull the squared out front, so I've got 4 pi r differentiating the first term. Now differentiating the second, I have minus 2,000 r to the negative 2. So I want to set that equal to 0. Well, how about, okay, yeah. I'm gonna write this now as 2,000 over r squared. Now, what I usually would do is to get a common denominator of r squared here, multiply by r squared over r squared, this term. I did a problem like this yesterday or the day before, and some of y'all were sort of uncomfortable with it. We don't absolutely have to do it that way. Is that all right? Are y'all okay?
We have to get rid of the r squared on the denominator.
Right, and it's because if I have a fraction equal to 0, then I know I can ignore the denominator because it means the top has to be 0. I'm not worried about having an r in the denominator. R can't be 0 or we wouldn't have can. You know, in these problems, that's what's nice, is at least you get to do practical stuff. You don't have to worry about things like if r is 0. That's ridiculous. Okay. So I'm going to put that over 1, set 0 equal to 4 pi r over 1 times r squared over r squared minus 2,000 over r squared. So 0 is 4 pi r cubed minus 2,000 all over r squared. Okay, now is where I either ignore the denominator, which I sort of like, or if that bothers you, multiply both sides by r squared. And 0 times it is still 0. So I now know that 0 is 4 pi r cubed minus 2,000. So 2,000 is 4 pi r cubed. So r cubed is, well, 2,000 divided by 4 is 500, isn't it?
Yes.
But I still have to divide by pi. So take the cube root of both sides because I want r alone. So I'm just going to leave it 500 over pi to the 1/3 power.
So why did you ignore the denominator?
Well, if a fraction is 0, and I've got a fraction set equal to 0, it means the top is 0, right? 0/3 or 0/10 or 0/5, that all means 0. So it's the denominator is just how many parts it's cut into. It's the numerator that tells you how many there are. So there we go. R is 500 over pi to the 1/3 power. Now, just like in the previous problem, we want to do a little check to tell us that this would be a minimum value for surface area. But that's, again, real easy, because if I took the second derivative, you could do the first derivative and do a sign chart on it. But in these problems, I don't know, for some reason, it's a little easier just to do a second derivative test, because you see how second derivative of this would be just 4 pi, and then -2 times -2,000 is positive 4,000, and then r to the -3, right? Okay, well, r to the -3 isn't negative, it just puts r cubed in the denominator, doesn't it? And r is a positive thing. So I have positive plus positive, and this therefore is always positive. But that implies it's always concave up, but that implies a min is 1. See, it doesn't take long to do these little checks, just to make sure we've got a min. That's enough. Okay, now I would like to know what the height is too. That's the other thing. We're not worried about volume. We know what the volume is, but we want to know the height and the radius. So that's the last of this problem. Well, we know that the height was this thing right here, 1,000 over pi r squared. Okay, now, so that's equal to 1,000 over pi times, all right, now r here is 500 over pi all to the 1/3 power. So we're gonna have to deal with that. Let's see, now, do you see this this kind of gives me an idea. Because I've got 500 here, and 500 is one factor of 1,000, so I might be able to combine something there if I write the 1,000 as 2 times 500.
You still have to square it to 500 pi.
And I have to square the 500 over pi. In fact, let's just write it to the 2/3 power. Thank you, Andrew. Okay? It's just the r that I'm squaring. And 500 pi to the 1/3 squared would be to the 2/3. Okay, we together now? Good? Okay, well, let's see. In the numerator, I'm going to write that as 2 times 500. In the denominator, I'm going to write it as pi over 1 times 500. Well, it's to the 2/3, and pi down here is also to the 2/3. Well, now, that's 2 times 500 over pi times, now we're dividing by this fraction and that's times the reciprocal, isn't it? I was uncomfortable with this fraction within the denominator of the fraction. So I left this pi here and I flipped that, okay? So h now is, well, okay, check this out. That's 500 to the 1 divided by 500 to the 2/3. Isn't that 500 to the 1/3? 1 minus 2/3? Okay? And then there's more pi is to the first down here and 2/3 up there. So really more of them stay in the denominator. So in the denominator, it would be pi to the 1 minus 2/3, 1/3. 2/3 minus 1, well, that'd be negative 1/3, but then it'd be in the numerator, so I'm putting it in the denominator. But isn't that, look at this. That's 2 times 500 over pi to the 1/3. Ta-da! That is 2r. We're out of the problem of thinking about just enclosing a liter. For any volume you name, if you want to minimize the surface area of the can, you make the height twice the radius. Period. This is powerful. Isn't that neat? All right, now, and we've proven it. We've proven it. So that's the power of optimization. The company could sit there and everybody could configure all these fancy shaped cylinders that they want to sell their drinks in, and that's fine, but they have to know going in they're spending more money than they need to on materials. And that's a choice. Stephen.
I was going to throw out there's an engineering constraint that we're learning about in engineering.
Mhm.
Typical industry has a cup holder of a certain size. So
Yep.
you built the can to have that size. And that's why you sometimes have taller cans, just to increase the volume without having to increase.
Yeah, because people will buy for their cup. I will buy for my cup holder. Yeah, I know that. Yeah. I buy cars according to how many cup holders. So anyway, I want you to think about this, and we will continue it tomorrow, and I appreciate your attention. Thank you.